Now let's use integration to solve differential equations. As a reminder, a differential equation is any equation that involves derivatives where the solution is a function. So for example, this is a differential equation. dy dx is 2x plus 3. That tells us that the derivative of our solution y has to be 2x plus 3. And also y of 1 equals 2. This is called an initial condition. We need this to find a specific solution, what's called a particular solution. This lets us find a particular solution. What that means is basically this. So there are infinite curves that have this for their derivative. Because when you integrate this, you get that plus c. And the plus c could be any real number. So infinite curves satisfy that differential equation, but only one of those will also have this condition. So that one solution is our particular solution. We want not the general solution that has this derivative, but the particular solution that has this derivative and that point. Furthermore, the solution to a differential equation has to be a continuous and differentiable curve. It's really this that's the big deal. Because of course, if a function is differentiable, it's also continuous. But we need it to be differentiable because if the derivative at any point does not exist in your solution, it means that this is not valid. Because the derivative has to exist in order for the differential equation to be true. So your solution cannot contain any discontinuities or any other points where you lose differentiability. So pretty much, here's the process. We start with the derivative. We integrate that because the integral of dy dx is y. This gives us our general solution. This is the family of curves that has the given derivative. We want the particular solution, so we plug our initial condition in. This says that when x is 1, y must be 2. We solve that out. We get c is negative 2. And so our particular solution is y equals x squared plus 3x minus 2. But before we circle that, we ask ourselves, do we lose continuity or differentiability anywhere? So to figure it out, we look first at our solution. It's a quadratic. Quadratics are differentiable everywhere. They're nice and smooth the entire way. There's no issues there. So our solution has no issues. We also go to the derivative, the differential expression. This is just a linear expression. Linear expressions have no continuity issues, which means we're good to go there. So this is valid for all real numbers from negative infinity to infinity. Because for the entire real number line, our function is continuous and differentiable, so there's no issues. But that is the process to solve a differential equation. You integrate the derivative, find the general solution, find c, think about your domain, which just means think of the solution or the differential expression have any differentiability or continuity issues. Let's try another one. dy dx equals 7 over xy with initial condition y of negative 1 equals negative 2. So here our differential expression, our differential equation is in terms of x and y. So our first step is to separate the variables. Because this is single variable calculus, which means we can't do integrals if there's two variables in them. So what we do is we write this in differential form, which remember just means moving that dx to this side. It looks like you're multiplying by dx, but you're not, you're just changing the form. But in order to do this derivative, we need just x's here. So we move this y over to that side. That is algebra. You multiply both sides by y. By doing that, we get y dy equals 7 over x dx. This we can work with. We have all of our y terms on one side, we have all of our x terms on the other side. We can integrate that. So we separate our variables first. Then we integrate. Y integrates to 1/2 y squared. 7 over x goes to 7 log absolute value of x plus c. We only put the plus c on the right side, because if we put it on both sides, there'd be like a plus c sub 1 and a plus c sub 2, and your first step would be to subtract those, which will give you a new constant called c sub 3. So rather than do all that work, we'll just put both constants of integration on this side, which makes sense because you want to solve for y, so might as well get everything away from y. Then we find c. Now, once you integrate, you can find c at any step. You can find c first, as I'm doing here. You could solve for y and then find c. As long as at some point you will find c, all is good. But I'm going to do it first. So we plug in -1 for x, and we set it equal to -2. So 1/2 -2 squared equals 7 log absolute value of -1 plus c. This one's actually kind of nice, because log of 1 is 0, which means c is just 1/2 -2 squared, which means c is 2. So we plug that in. 1/2 y squared equals 7 log absolute value of x plus 2. And now we want to solve for y. When you see this question on a quiz or a PSET or an exam, the question, which I did actually not give here, I should have actually asked the question. The question will say, I'll put it in blue, find the particular solution y equals f of x such that ... So you want to find the particular solution y is a function of x such that the derivative is this and this points on it. So the question wants you to solve for y. It wants y as a function of x. So we do that next. First we multiply everything by 2. So y squared equals 14 log absolute value of x plus 4. I'm just going to write that over again. My pen's slowly dying. So going to a new page. Y squared equals 14 log absolute value of x plus 4. Then to solve for y, we take the square root of both sides. But remember, when you take the square root of both sides, it's plus or minus, because both a positive and a negative will square to a positive. Our particular solution can't be both positive and a negative square root, because that will not be a function. We need only one of those. So to see if we have a positive or a negative in front, we go back to our initial condition. The initial condition was y of -1 equals -2. That means that we had a negative answer, which means we have to have the negative square root. So our solution is y equals negative root 14 log absolute value of x plus 4. Let me write that again, because again my pen isn't doing too hot. There you go, that's written out better. Now for the domain. Are there any issues with continuity and differentiability? That answer is a big yes. There's a whole bunch of things going on here. First, let's check out the differential expression. We started off with that right here. As we can see, x can't be 0 and y can't be 0. Because if we have x is 0 or y is 0, our derivative does not exist, which means this is not true. So, x can't be 0 and y can't be 0. Good to know. And now for our solution. As a quick side note, actually, our solution can only be one differentiable curve. So since x can't be 0, that means that right now x can either be less than 0 or x can be greater than 0. It's just one or the other. We can't have both in our domain. The domain has to be one continuous curve. So it's one of those two. From our solution, we have a radical. A radical has a constraint that the inside cannot be less than 0. So we need that to be greater than or equal to 0. So we solve that out. Subtract 4 and divide by 14. Gives you this right here. Do e raised to both sides. And we have this expression right here. We just did e raised to both sides. To solve this inequality, if the absolute value of x is greater than or equal to this number, it means two things. One is either positive x is greater than or equal to that number, or two, it means that on the negative side, you are more than that in terms of size, which means if you're negative, that you are less than or equal to negative e to the negative 2/7. Why that makes sense, it might be good to go to a simpler example. Let's say that you had absolute value of x was greater than or equal to 4. This means that the size of your number is bigger than 4, because absolute value tells you how big the number is. So if you're greater than or equal to 4, your size is bigger than 4. But also if you're past negative 4, if your number was negative 6, the size of that number is 6, which is bigger than negative 4. So this expression turned into this piecewise expression, which makes sense since absolute value is a piecewise function. And so we did the same thing here, just with a harder to picture number. And so now we put all of our conditions back into each other. So we can only be either greater than this number or less than that number. Now, again, our initial condition comes into play. Our x value is -1. -1 has to be in our domain of our function because that was our point to start with. -1 is not in this domain, so it can't be our answer. -1 is in here, because -1 is less than negative e to the negative 2/7. So that's good to go. So that's going to be that one of those. We now know that we don't need either of those two, because x less than 0 is kind of included in this. This is the more strict version of that. Y can't be 0. It means that we can't have equality, because if x equals negative e to the negative 2/7, this whole thing is 0, which means y is 0. But we can't have that. So our domain is x is less than e to the negative 2/7. A lot of times finding the domain is the hardest part of the problem, because it's not as formulaic. The rest of the question is pretty formulaic. You have your expression, you separate your variables so you can integrate, you find c, and you solve for y. And then once you have y, then you think of your domain. And again, you look at two things: your final solution and see what constraints that has, and your original differential equation and see what constraints that has. And then you figure out which of those constraints also includes your initial point, and that's your answer. Again, use the notes on Stellar, because I typed up the solution to this, and it might be easier to understand in written form.